Hello everyone. So we are going to start the part 2 of flow of fluids. So here we are going to study the Bernoullis Theorem, the derivation of Bernoullis Theorem, and different types of manometers which are used to actually calculate the differences in the pressure. So without wasting any time, let's start the Bernoullis Theorem. So regarding the Bernoullis Theorem, you see, so Bernoullis was a pioneer in science. Moreover, his interest was basically in medicine as well as in the engineering. So Sir Bernoullis, along with Euler, they have investigated the relationship between the pressure and the velocity of fluid. They have togetherly investigated the relationship between the pressure and the velocity in terms of fluid. So what actually they have done? They have done a simple experiment earlier. What they have done? They have simply punctured a pipe with a straw and observed the height of the liquid in the straw. And they have found that there is a relationship, or you can say there is a correlationship between the pressure of the fluid, flowing in the pipe, moreover the height of the fluid which is coming out of the straw. So this is a very simple experiment. So in our practical aspect we can show it like suppose there is a pipe, there is an iron pipe which is carrying the water, right? If in that iron pipe, if we make some hole, right, and we put one straw perpendicularly straightward, if we put one straw in that pipe perpendicularly, the height of the fluid which is coming out from the straw which has been put perpendicularly by making a hole in the pipe carrying a fluid, it is related, the height, it is related with that of the velocity, or you can say that of the pressure of the fluid which is there in the pipe. Thus, what they have done, they have used this particular relationship to measure the blood pressure, where they have tried to puncture the capillaries, or you can say they have tried to puncture the blood vessel with the glass capillaries. Now you know that in our blood vessels the blood, it is flowing, right? The blood is having a pressure. What is pressure of the blood? It is the pressure which is exerted by the blood on the wall of the vessel. That vessel can be either your artery or the vein. Now if we puncture this artery or the vein with a glass capillary, the blood will come out from the capillary. Now the height of the blood which is coming out from the capillary, it is associated with the pressure. So generally we have two pressure in our blood vessel. One, it is known as the systolic pressure, which is equivalent to, or which is corresponding to 120 mm Hg. Another one, it is the diastolic pressure, which is corresponding to 80 mm Hg, right? Now you see the Bernoullis theorem. So what is Bernoullis theorem? Basically, let us consider a tube. So this is a tube with a varying diameter. Suppose here the diameter is more, here the diameter is less, right? So it is having two heights. Suppose this is the height y1, this is the height y1, and this is the height y2. They are having the fluid at different height, right? And a fluid, it is allowed to flow through this pipe. The thing is that the fluid which is allowed to flow through this pipe, it is incompressible. It don't get compressed while flowing. Now the relationship between the area of the cross section A, so this is the suppose overall area A. So here the area of cross section, it is denoted with A2. Here the area of cross section, it is denoted with A1. Now the relationship between the area of cross section, the flow of the fluid, the flow speed, it is designated with V. Here it is the change in the flow speed, that is the delta V or dV. Here again there is a change in the flow, this is dV, right? Now the flow of the fluid through this vessel, it is V, right? And there is a height. This pipe, it is at somehow a height from the ground. Suppose this is the level of the ground, so this is the height. Here the fluid, it is at a height of y1. Here the fluid, it is at a height of y2, and the pressure at the 2.1 and 2. So this is the point 1 and this is the point 2. The pressure are designated as P1 and P2. So let's start the derivation of the Bernoullis theorem. So basically there is some assumption in Bernoullis theorem. The first assumption is that the density of the incompressible fluid, the density, that is the rho, the density of the incompressible fluid, it remains constant at the both point. As per the theorem, the density of the fluid which is coming at the point A and which is leaving at the point A2, this is the A1, this is the A2, the density will remain as it is throughout the flow, right? Moreover, the energy of the fluid is conserved. Here we are going to apply the law of conservation of energy. So as per the law of conservation of energy, the energy of the fluid is conserved, because as per the law of conservation of energy, the energy, it can be neither created nor it can be destroyed, right? It can be only changed from one form to another. So here we are going to apply the law of conservation of energy. So therefore, work done on the fluid, here we need to do some work so that the fluid will come out from if the fluid, it is coming in at the point A1 and if it is going out at the point A2, then here we need to do some work. So work done, small amount of the work is, that's why we are using small d. Small amount of the work done is equal to F1. F1, it is the force applied at the point A1 into dx1. x1, here this is the distance dx1. In this distance, in this particular, from this, starting from this point ending at this point, this is the amount of the force applied, because we know that work done is equal to force into distance, right? So here force we have applied F1, right? And the distance converse during this force, it is dx1. So the work done is equal to F1 dx1, initial force we have given, and minus, work done is equal to minus F2 dx2. Here this is the force which is going out, right? Now we know that the force can be written as, pressure applied over the area. Thus you can say F1 can be written as the P1, this is the pressure 1, into A1, right? This is the area 1, right? Or area of cross section A1, and dx1, this is the distance, is equal to here similarly A2 dx2 P2, right? Now here we simply take out the P1, right? So P1, area into distance, it is nothing but area into length. This is the length, right? Area into length is nothing but it is the volume. It is the volume. Area into length, it is the volume. So here we have taken the volume. So taking the volume as constant out, it is simply the amount of the work done is simply P1 minus P2 into the change of the volume, right? Now you see again, we know that the work done on the fluid, whatever amount of the work done on the fluid, was due to conservation of gravitational force. As there is gravitational force, how gravitational force will act? Gravitational force will act by virtue of potential energy, as because this fluid, it is at some height, here it is at some height. So here the energy, potential energy, is equal to mass into, generally F is equal to m into a, right? So mass, where a is the acceleration due to gravity, so you can replace a with small g, right? So we know that the fluid was due to the conservation of gravitational force and change in the kinetic energy. Thus you can say that change in the kinetic energy of the fluid is given as kinetic energy formula, it is simply half mv square, right? So here you see the change of the kinetic energy between these 2 points. Suppose it is simply half m2 it is the mass of the fluid here, into v2 square. V2 it is the velocity of the fluid at this point, 2 v2 square minus half m1 v1 square. So here m1 is the initial mass and v1 it is the initial velocity. Thus you can take out the rho. Mass is nothing but, mass is simply density into volume. So here we are going to keep density into volume, change in the volume, and v2 square minus v1 square. Then similarly, change in the potential energy can be given as simple change in the potential energy, delta U is equal to mgy2. So here y2 it is the distance here from the ground. This is the distance y2. This is the y2 distance of the fluid from the ground, right? And this is the y1 distance of the fluid from the ground. So mass into force, right? The mass of the liquid into acceleration due to gravity into the height. Thus you can see again, this is the change in the potential energy, which is equal to, mass can be written as rho into dV, that is the density into volume, into g y2 minus y1. Done. So now the energy equation can be now given as simply dW, it is the amount of the work done. I repeat, dW is the amount of the work done. We have already performed some work over here, right? Is equal to change in the kinetic energy, that is the dk, and plus change of the potential energy. Thus you can write this as work done is can be written as, we have already derived this part, right? Is equal to change in the potential energy plus change in the kinetic energy plus change of the potential energy. Thus you can rearrange it just like that, P1 minus P2, you can just rearrange it, just taking the dV common in both sides, you can cancel out the dV. Thus after rearranging the equation you can get, just bring out the V1 in this side. Thus you can say P1 plus half rho V1 square plus rho Gy1. So this is the energy, or here it is the pressure energy, this is the kinetic energy, this is the potential energy. At this point it is equal to this point, and this equation is nothing but, this is the Bernoullis equation, right? Now you see where the Bernoullis theorem it is applied. So basically the Bernoullis theorem it is applied in the measurement of the rate of fluid flow. If somebody asks you to find out the rate of fluid flow, we use or we apply the Bernoullis theorem. Moreover, it is applied in the working of the centrifugal pump, and in this the kinetic energy is converted into the pressure. So centrifugal pump, it is a very common pump which is used in the pharmaceutical operation. So in our consecutive slide, when the use of centrifugal pump will come, I will definitely elaborate how it works, right? Now during this process, actually during the flow of fluid, actually we encounter different type of energy losses. Now these energy are lost because if we start the flow of the fluid at the point A1, and if it is coming out at the point A2, the amount of the energy is somehow get losses. So there are different types of energy losses in the fluid flow. So according to the law of conservation of energy, we know that the energy balance has to be properly calculated, right? Because as some form of the energy will get converted into some other form. So basically we have the fluid, they experiences energy losses in 4 basic types actually when they flow through a pipe. So types of the energy losses: number 1, frictional losses. The loss of the energy, they occur due to the friction of the fluid with that of the wall of the pipe. This is known as the frictional losses. The next loss is due to the losses due to the fittings. When we all have observed that in our household also, when a plumber he used to work, after some covering some distance, the plumber they used to use some sort of fittings. Now these fittings actually they causes of loss of energy of the fluid. So we are going to calculate, we are going in brief. Next is the loss due to the enlargement. Sometimes the diameter of the pipe may be, somewhere it is maybe less, somewhere it may be more. So if it is coming from a small diameter to a large diameter, automatically the flow of the fluid will come down. As the diameter it enlarges. So this is known as the enlargement loss. And we have the contraction loss. Similarly, if the fluid is coming from a bigger pipe, bigger size pipe, and it is converging to a smaller size pipe, then also there will be loss of energy, which is known as the contraction losses. So let's start with the frictional losses, how it takes place. So during the flow of fluid, the frictional losses, it causes loss of the pressure. So this friction actually causes the loss of the pressure. So the type of the fluid flow, it influences the losses. So in general, there will be a pressure drop down due to the friction. Whenever a fluid it will flow through a pipe, there will be always a pressure drop down. There will be always a pressure drop down due to the frictional losses. So the pressure drop down, it has been found directly proportional. This is not alpha, this is directly proportional side. It is directly proportional to the velocity. The pressure drop is directly proportional to the velocity of the fluid flowing through the pipe. Moreover, it is directly proportional to the density of the fluid. It is directly proportional to the length of the pipe. It is inversely proportional to the diameter of the pipe. So here we are going to create one relationship between the pressure drop down and frictional losses. Thus this relationship, it is actually proposed by Fanning's, and this equation, it is known as Fanning equation for calculating the frictional losses. So as per the Fanning's equation, the pressure drop down, it is directly proportional to this. So 2 into F, here it is the frictional loss. Delta P, it is the change of the pressure or pressure drop down. F, it is the frictional loss, right? Where U is the velocity, L is the length of the pipe, rho, it is the density of the fluid, divided by D, it is the diameter of the pipe, right? So this is the Fanning equation. So F, it is known as the frictional factor. Thus for viscous flow pressure drop, suppose you are using a viscous fluid, then we use Hagen-Poiseuille equation, and as per Hagen-Poiseuille equation, this pressure drop down is equal to 32 ln, this is actually mu, this is eta divided by d square. So everything is here only, right? Velocity, length into velocity, where this is the drop down, frictional drop down, and this is the diameter. The next one, it is the losses in fittings. So there are some losses in fittings. So we know that the Fanning's equation, it is applicable for losses in the straight pipe. As per the Fanning's equation, we can apply the Fanning's equation for losses of energy in the straight pipe when fittings are introduced in a straight pipe. So these fittings actually, they causes the disturbances in the flow of fluid through a pipe, and which results in the additional loss of energy due to the, when you are going to apply some fitting, so there is additional loss of energy in the pressure, or you can say force of the fluid. So the losses in the fittings may be due to change in the direction. Suppose there is an angle which is introduced in the pipe. So earlier it was moving in a suppose in one direction, then you have put one L type of angle, then it will take straight sharp, or you can say it will take 90 degree in the movement. So if there is a change in the direction, there also you will find change in the, or you can say loss of the energy. Moreover, the change in the type of fitting. So basically you see, this is a very simple fitting which you can observe in our household pipe and fittings, even in our institute also, right? So this type of fitting, it is known as T fitting, and its equivalent length, it is 90 cm, right? Now this is known as a globe valve, which equivalent length is 300. So simply we have a formula that the equivalent length of the fitting, is equal to the equivalent length, this is the equivalent length, into internal diameter, Suppose let's calculate for the globe valve. So in the globe valve, you see the equivalent length is 300 into internal diameter of the globe valve is 50, so we have 15 meter. Equivalent length of the fitting should be 15 meter. Thus, this means that the globe valve is equal to 15 meter straight line, right? This is the demonstration of the side, 15 meter straight line. So its length is substituted in Fanning's equation. Thus, here for globe valves, this length can be substituted with 15 here, right? The next one, it is the enlargement losses. So enlargement losses, it occurs when the fluid it is flowing. Earlier it will be flowing through a pipe of the lower diameter, and gradually it is introduced in a pipe of bigger diameter, bigger size. Then enlargement will take place, and due to which there will be loss of the energy. It is known as the enlargement losses. So if the cross section of the pipe it enlarges gradually, the fluid it adapts itself to the change section without any disturbance. So generally there is no loss of energy. So earlier you see here, this is the mu1, you can say earlier initial velocity, this is the mu2, right? So now there are the difference in the velocity. So if the cross section of the pipe it changes suddenly, then the loss is observed due to the eddies. Eddies means nothing but it's the turbulent. Eddies or turbulent, it is the same thing only. So when you force some liquid from a smaller pipe to a bigger pipe, you will find turbulence, right? So here these are greater at this point than the straight line. So eddies are more at this point. Eddies are more at this point as compared to the straight line here. Eddies are more at this point, right? So now we know that the mu2, this velocity, it is lesser than mu1, earlier velocity, because here the size has increased. Here the size has increased, thus the pressure has come down, or the liquid has become relaxed, right? So for sudden enlargement, there is a formula. For sudden enlargement, you can simply calculate it, the loss of heat, or you can say loss of energy can be calculated as the mu1 minus mu2 whole square divided by 2g. This is the loss, or you can say delta H is nothing but it is the loss heat due to the sudden enlargement. This is the formula which is used to calculate the loss of the energy due to enlargement, right? Now the next thing is contraction losses. Now what is contraction losses? When the pipe it has come from a bigger size. Now suppose earlier the fluid it is flowing through a bigger pipe. Now it has come to a smaller pipe, right? This is known as the contraction loss. So if the cross section of the pipe it is reduced suddenly, the fluid flow is disturbed, right? Now the diameter of the fluid stream is less than the initial value of the diameter, and this point of minimum cross section it is known as vena contracta. I will show you which is vena contracta. And the velocity of the fluid here in the smaller pipe it will be now greater. Earlier mu2 was greater, here earlier mu1 was greater, here mu2 will be greater, the final velocity will be greater. So this is the vena contracta, bigger pipe, this is the smaller pipe, and this is the contraction, this is the vena contracta. So here you can see the u1 may be considered negligible. Thus you see here the loss due to additional eddying are observed here. So such sudden contraction losses can be defined as here as a k mu2 square divided by 2g, where mu2 is the velocity, k is the constant, h is the loss due to sudden contraction. Clear? So next is manometers. So manometers, what are manometers? Manometers are the devices which are used for measuring the pressure difference. Manometers are used for measuring the pressure difference between 2 points. So different types of manometer we use in pharmaceutical engineering. They are the simple manometer, we have the differential manometer, moreover we have the inclined manometer. There are 3 types of the manometer which are very commonly used in the pharmaceutical engineering. So let's go with the first one, that is the simple manometer. So this is a simple manometer. So here, this manometer, it is a very commonly used manometer. Moreover, let's see the construction. Here, I have divided the whole manometer into different points. This is the point 1, point 2, point 3, point 4, and point 5. Suppose here we have applied a pressure P1, and here we have applied a pressure P2. Here you have two immiscible liquid. One, it is the liquid A, which is in red color, and the one it is the liquid B, which is in white color, right? Now you see, it consists of a U tube. This is a U tube, U-shaped tube, right? It is filled with the liquid A. This is the liquid A with the density of rho A. Unit is kg per meter cube, and above which there is a arm, or above A arm there is a liquid. This is the liquid B, which is having a density of rho B, right? So you think, or you have to assume that this liquid A and liquid B, these are immiscible. So you can clearly demarcate. Liquid A, it is red in color, liquid B, it is white in color, right? Now, if the two different pressures are applied, here pressure P1 we are applying, here pressure P2 we are applying, right? Are applied on the two arms of the meniscus, one liquid will be higher than the other liquid. So here, if you are applying pressure, you see this meniscus, it is higher here. So let's calculate the pressure difference. How we are going to calculate? So again, that is the diagram. Now let us consider that the pressure at the point 1, it is to be P1 Pascal, and the pressure in the point 5 will be P2 Pascal, right? The distance between this is M, between 4 and 5, and distance between 4 and 3, it is R, right? So now you see the pressure at the point 2. This point can be written as, at this point the pressure can be written as simply, we are applying a pressure P1, right? P1 plus the distance. This liquid B also applying the pressure, right? What is the distance of the liquid B? M plus R. This is the distance, right? Into its specific gravity, or you can say density, right? Its density, and this is the gravitational force. This is the acceleration. Now it is giving a pressure. So at this point you are having two pressure. One due to the pressure 1, or you can say P1. The other one is due to this liquid. This liquid, it is M plus R, the distance M plus R into the density of liquid B into acceleration due to gravity, it is coming down, right? Now, since we know that, we have already derived that change of the pressure is equal to the delta P is equal to delta H rho G, right? We have already derived in our previous class. So here you see M plus R is what? M plus R is simply the distance between 3 and 5, right? Does you see, since the point 3 and 2, they are at the same height. These 2 point and 3 point, they are at the same height. We know that, right? So you see pressure at the point 3 here also, you can write it as P1, as it is the P1 pressure, right? M plus R, similarly like this, M plus R rho B into G. At these 2 points the pressure will be same, right? Now the pressure at the point 4, at this, what will be the pressure? And the pressure at the point 4, it is less than the pressure at the point 3, because due to the distance R. Here the pressure will be less, here the pressure will be more, because this fluid is also applying the pressure at the point 3. Thus the pressure at the point 4, it is less than pressure at the point 3 by R. R is the distance, rho A, rho A, it is the density of the liquid A into G. Thus you see the pressure at the point 5, at this point, is less than the pressure at the point 4. Here, what is the difference of the pressure? Simply distance M, right, and density of B, that is rho B, right, and into G. So this is the difference. Now you see this overall thing can be manipulated or can be rearranged in this way. P1 here, P1 m plus r, right, into rho b, this is the rho b, into g, right, minus, again you minus it, minus r, this one r, into rho a, this one, into g, right, minus again here m, right, into rho b into g, thus you can say is equal to P2. So this is the simple manometer. Here we are going to calculate the pressure at the two different point by using, because now you can ask me, how will come to know the density? You definitely will be provided the density, and the density is not provided, definitely you will be provided with the amount of the pressure that has been applied here. So simply change of the pressure is delta P is equal to P1 minus P2 is equal to R, right? R, it is the distance, right? Rho A minus rho B into G. Thus, application of the simple manometer, simply it is used to find the pressure differences, and that is determined by measuring the R, right? Moreover, the manometers, they are used in measuring the fluid flow, or you can say flow of fluid, right? The next type of manometer, it is the differential manometer. So here again you see we are applying here pressure P1, here pressure P2. These are the different point 1, 2, 3, 4, 5, 6, 7, right? This is the fluid, it is filled with this white color, it is filled with the fluid B. This is the fluid, it is filled with the fluid A, or you can say it's a liquid A, and this is the liquid C. Here you can see the size of the pipe, it is more here, it is enlarged here at this point, right? This is the distance, just like the similar one, earlier one. The distance between this point to this point, it is D. Distance between this to this, it is A, and distance between this to this, it is R. Simply here these manometers, they are suitable for measurement of small pressure differences, right? So differential manometer, they are also known as two fluid U-tube manometer. They are also known as two fluid U-tube manometer, right? So it contains actually basically the differential manometer, it contains basically liquids A and liquid B having nearly same, the liquid B, or you can say fluid B and fluid A, they are having nearly same density, right? The U-tube, this is the U-tube, U-shaped tube, it have a enlarged chamber on the both the limb. Limb means the feet, it have a enlarged chamber here, right? Using the principle of simple manometer which we have studied earlier, the pressure difference can be also calculated here. Simply change in the pressure is equal to P1 minus P2. This 2 point P1 minus P2 is equal to R. R is the distance, right? And rho C here, this is the rho is the density of the liquid C minus rho A. So this is the density of the liquid A, right, into G. So this is the differential manometer. So hence you know that smaller the difference between the rho C and the rho A, larger will be the R. Smaller the difference between the density of liquid C and liquid A, greater will be the distance R, right? Now the next type of manometer is known as inclined manometer. It is having, or it is put in some angle actually. So many of the application, it required accurate measurement of low pressure, accurate measurement of the low pressure, not the high pressure, such as draft and very low differential. So primarily it is used in the gas, or you can say air and gas installation. We use the inclined manometer. So how it works, simply in this application, manometer is arranged with the indicating tube inclined. So this inclined manometer, it enables the measurement of small pressure changes with increased accuracy. Simply how it measure P1 minus P2, that is the change in the pressure at the 2 point. You can also designate it with delta P, right, is equal to small g R rho A minus rho B. That is density of A minus density of B into here. This is sine alpha. sine alpha. Now where the sine alpha has come, because I have already described here the term inclined. It is inclined with some angle, so that angle, that sine value of that angle. So here you can see, simply to measure the small pressure difference, it is used to magnify the Rm. So this is the pressure. Suppose here the pressure is Pa, here the pressure is P2, right? This is the distance. So this is the plane horizontal line, right? So here if we see the distance, this is the distance. If we consider here Rm, it is the simple inclination. Rm, it is the simple inclination at this point, and this is the R1. It is the simple inclination at that point, and the alpha value. Now this alpha value, we will have to take one arbitrary line here, and this is the angle alpha. So simply change of the pressure Pa minus Pb is equal to G into R1. This is the R1. From here to here, this is the R1. This distance, it is the R1. Again, Pa minus Pb into sine alpha. This is the angle sine alpha. So here you are going to get the small pressure differences between 2 points. Thus, lastly, thank you everyone for your patience hearing. If you like the video, just press the like icon. You can share this video with your classmates, and for further notification from this channel, you can subscribe my channel. Thank you once again.